Welcome everyone. This will be an interactive talk, and we begin with a discussion about these three pictures. My first question for you is, what do they have in common? What feature do you see which is shared by all three of these pictures? Yes?
They're all lines connected, no, dots connected by lines.
Oh, very good. They are all dots connected by lines. Very good. Yes? Yes?
They're all black and white.
All black and white, yes?
All two dimensions.
2 dimensions, all of them are in the plane. Very good. Yes?
If you start on one node, you can hit every other node.
If you start in any node, these points you call nodes, you can go to any other by following the curves. Very good. We say that all of them are connected configurations. You can go from every point to every other point following the picture. Yes?
The lines don't cross.
The lines never cross. Very good. They connect a point with a point and they never cross. Excellent. Great observations. Yes?
They are all closed.
They are all closed. What do you mean by that?
Well, they are closed figures, like, I don't know, a triangle and...
Aha, they are all they're all enclosed in a certain way. Yes. That's true. I would put it differently. They all have an exterior region. Yes. They all enclose a certain shape. Very good. Yes. Other observations? So far, very good. You said that they're made out of points and lines. Now let's agree on our terminology. The points we're going to call vertices. This is one vertex. And what you call lines or curves, I would call them, we are going to call them edges. Okay, other observations? What are they made out of? They're made out of these points and edges. This is the skeleton, yes?
Yeah, the edges are sometimes curved and sometimes straight.
The edges are sometimes straight, sometimes curved, yes, that's true. Yes. What other entities do you notice on the picture, except the vertices and edges? Yes?
The edges
The edges
bound an area.
bound areas, exactly. So any of these regions we're going to call faces. We can call them regions, but let's agree to call them faces. So it's all of the pictures are made out of vertices, edges, and the edges bound these faces. Okay, excellent. These are great observations. All three pictures have that, and these are qualitative observations. They are based on what you observe. Now, we're mathematicians. This is a mathematical talk. We like numbers. We have to get to numbers. We're not painters. So let's bring in some quantitative observations about these pictures. Quantitative means something that you count, some numerical value, some numbers. We should get some numbers out there, yes? Okay, very good. On the first picture, you have 6 vertices. One thing that you can count is the number of vertices. Yes?
On the second one, each circle has 6.
On the second one, there are 6 on each of these circles, but the circle shape is somehow very specific to the second picture. We're eventually trying to figure out what all 3 of them have in common. But very good, you count the vertices. Now, continue in this spirit. What else would you do? If you want to get quantitative information, yes?
You count the surfaces.
You count the surfaces or the faces. Yes, but even before the faces, yes?
You can, a dot is always, a vertex is always connected to between 1 and 4 edges.
Aha, you can count how many edges go out of a vertex. Very good, that's also something that you can count. Now suddenly you see there are so many things that you can count. Suddenly it's full of things that you can count. Let's count. What would be the next thing to count after the vertices? Yes? Edges, let's count the edges. How many are there on the first picture? 7. Okay, 7 edges. And then, as you suggested, we also count the faces. So these are things that we can count. The second picture doesn't have 6 vertices. So the number of vertices is not common among all the pictures. But let's do these counts for all the pictures, nevertheless. What about the second picture? How many vertices are there? 13. How many edges? You have to find some way to count. 24. And how many faces? Yes? 13. Okay, very good. Now, do the numbers below the first picture have anything to do with the numbers below the second one? Or do they seem independent? They seem independent. Now let's do the third picture as well. Let's do the count for the third picture. How many vertices? 6. Edges? 9. And faces? Okay, 5 faces. By the way, when we count the faces, you said there are 3 faces on the first picture. One is this diamond face, then the other one is the weird one. There is also the exterior face, the outside face, the region outside of the picture. We decided to call this a face as well. Right now you have to choose if you call it a face or not. It's different from the other faces. It looks very different. It's unbounded. It goes in all directions. It's exterior. It's on the outside. But we decided also to count it in. And by the end of the talk, it will be completely obvious to you that there is a good reason why we include this face in the count. Okay, so these are the counts. We have collected the data. Now, go back to the question. What do the 3 pictures have in common? Now, give me something quantitative. Yes?
If you subtract the number of edges with the numbers of vertices, you get the number of faces plus 2.
Very good, very good, very good. If you subtract the number of edges from the number of vertices plus the number of faces, you always get 2. 6 plus 3, if you add them up and subtract 7, you get 2. 13 plus 13 minus 24, you get 2. 6 plus 5, if you subtract 9, you get 2. Excellent. The numbers are different. The counts are different in all pictures. But at the end, when you do this arithmetic, you always get 2. This number 2 is what the 3 pictures share. They all have the same number 2 after you do this arithmetic. Now, for a certain reason, I prefer to write vertices minus edges plus faces. Put the edges in the middle with a minus. Okay, very good. So for us, a plane drawing will be a configuration like that, as you say, consisting of vertices, edges, and faces. Crossings of the edges are not allowed, as you observed. And the disconnected configuration is not allowed either. The reason, you made the observation that all of the previous drawings were connected. The reason we don't want to allow this is that here the beautiful formula fails. Here you have 3 plus 4, 7 vertices, 5 edges, and only 1 face. And the formula fails because you have 7 minus 5 plus 1 is equal to 3 at the end of the day. That's why this is not allowed. It has to be like this. That's what we're going to call a plane drawing. Now, let's denote by V the number of vertices, by E the number of edges, and F the number of faces. Throughout the whole talk, these 3 letters will represent vertices, edges, and faces. Now, as you observed, if you compute V minus E plus F, a miracle happens. Now, what is V in this case? Yes? 8. What is E? If you figure out how to count it, it's not... Yes? Edges. Edges. E stands for edges. Yes? 11. And how about the faces? As you say, 5. And when you do this, we call it an alternating sum. You start with plus, then minus, and then plus again. Again, you get a 2. This is a theorem discovered by Euler in the middle of the 18th century, and just rediscovered by you a while ago. V minus E plus F is always equal to 2 for any such plane drawing. This is a remarkable formula because of its simplicity. You see, it only involves the 3 quantities that show up naturally. These were the 3 things that you wanted to count. And the 3 things you wanted to count are combined in this way, by this relationship. And the formula involves only addition and subtraction. Can't be anything simpler than that. We're going to prove this theorem. So we're going to understand why it always holds for any plane drawing. It's definitely not obvious that if I draw some crazy plane drawing with many vertices, many edges, many faces, why does this formula always hold? Well, we're going to prove it. And to prove it, we'll think of it not as visitors in a museum. You go to a museum and you look at some painting and you look at it and you wonder how it appeared and it's a marvelous painting for you. Rather than look at it as a visitor in a museum, we think of it as the painters who drew it, who made it. So think of this as if you're the engineer, you're the architect who makes it. Namely, you start with only one edge at the beginning. You're going to construct the picture from scratch. Start with just one edge. And let's check Euler's formula. You have 2 vertices, you have one edge, and you have only one face, this outside face. Certainly the formula holds. 2 minus 1 plus 1 is equal to 2. And then, what would happen if you were to draw another edge, like that? Well, if you were to draw this edge, the number of vertices increases by 1. You add an extra vertex. The number of edges increases by 1. You add this extra red edge. And the number of faces does not change. You still have one face. You used to have one face, and you still have exactly one face. So what happens is, in this way, you increase both V and E by 1. And in the formula, V comes with a plus, E comes with a minus. So if you increase V and E by the same quantity, in this case by 1, the expression V minus E does not change. F doesn't change anyway, so the whole thing doesn't change. V and E changed, now they're 3 and 2, but the whole expression does not change, it still equals 2. Now, if you were to draw another edge, again, V and E both increase by 1, but because they have negative contributions, opposite contributions in the formula, you do not destroy the formula. You can keep going, you can draw the next edge. Again a new vertex, again a new edge, no more new regions, again one region. So the vertices from 4 and 3 will change to 5 and 4, but the formula will still hold true. Okay, you keep drawing it. Now something different happens if you connect these 2 vertices. What is happening now? Yes?
When you make a new edge, normally there is a new vertex as well, but in this case there is a new vertex, so there is a new face.
Very good. Normally, so what happened so far, when you draw a new edge, you introduce a new vertex. Here you don't introduce a new vertex, so the vertices stay the same. You do introduce a new edge, but this time you create a new face. When you connect those 2, you bound this region, so you create one interior region and you have the exterior region. Now you're going to have one more face. What happens is you increase both E and F by 1, by the same quantity, but watch out, in the formula, E and F come with opposite signs. So when you increase both of them by 1, the total expression does not change. You do not change V. So this is a second type of edge that you can draw, connecting two already drawn, two vertices already drawn. What would happen if you join these two by an edge? What would happen with the numbers of vertices, edges, and faces? Yes? The formula wouldn't be true because you add two vertices but only one edge. Very good. You create two new vertices, one new edge, and no new faces. In this case, the formula would fail because you increase v by 2, but e you increase by 1. And the formula will give you a 3. What is wrong here? Why did the formula fail? Yes?
Couldn't you say that, like, if you subtract 1 from the formula at the end, you get the number of independent paintings?
Independent components, yes. You can modify, that's one way to rescue. You can modify the formula by also putting inside the formula the number of independent, as you call them, or connected components. That's true. So you can rescue the formula by adding another term. Or, let's just stick with the formula to contain only v, e, and f. How would you rescue this? We're nervous about this slide here. We don't want it. What is wrong, yes? It has to be connected, very good. By a plane drawing, we understood something connected, and this is not connected. If we draw this edge, it's not connected. So as you say, follow the instructions and keep it always connected. We cannot finish the proof from here, because now the formula will break. If we keep drawing the picture, at the end we saw the formula holds at the end. So at some point the formula will get recovered. But it's much harder to prove, okay, it holds at the beginning, it holds for a while, then it breaks, and then to prove that it recovers. That's much harder. It's much easier to keep yourself healthy rather than get sick and then recover. So here, we just don't want to do that. Our strategy for the proof, therefore, will be draw one edge at a time, as we've been doing, but always keeping the drawing connected. Always draw an edge starting at a vertex that has already been drawn, either to a vertex that is new or to a vertex that has also been drawn. This will be our strategy. So now, for example, this is allowed. We can draw this edge. In this way, we increase vertices and edges by 1. No new regions are created. And the formula continues to hold. If you connect these two, now you connect two vertices already drawn. You introduce a new face and a new edge, but no new vertex. So +1 contribution for both E and F. On each step, E increases by 1, and then either V increases by 1 as well, and F stays the same, or V stays the same, and F gets increased by 1. Here. If you connect this, now you can connect that. Now you can draw this edge, because now the configuration will stay connected. You increase V and T by 1. Here you will introduce a new face. Here a new vertex. And finally, can you make a general argument? Why is it always the case that if you connect two vertices already drawn by an edge, you always bound a new face? If you have two vertices already drawn, as here, and if you connect them, you always create a new face. On the picture it's obvious, but can you make a general argument, yes?
Because the two vertices are always connected.
Very good, because the configuration is connected, and if you have two vertices already drawn, there is a path from one to the other, and when you join them, then you're going to bound a region. Very good. We are using in a crucial way that the configuration is connected at all times. Okay, so finally, we arrive at these numbers 8, 11, and 5. At the beginning, you counted them, and the formula, you observed the formula is satisfied. Now you are like this engineer or architect who knows what's going on behind. Now, if you look at a skyscraper, like, why does this thing not fall in earthquakes? But if you are the engineer, you know why, because you constructed it. Similarly, we started with 2 vertices, 1 edge, and 1 face, and build it up step by step to the numbers 8, 11, and 5. They're not completely random numbers. They are obtained from the initial tree by increasing either V and E at the same time by 1, or E and F at the same time by 1. Okay, this proves Euler's formula. Did any one of you know this formula from before? Yes? A couple of you? Okay, very good. Very good. Now we'll continue further. Let's look at these three-dimensional objects, these polyhedra. Tetrahedron, cube with a roof on top, and a triangular prism. You can call it a Toblerone if you want. What do they all have in common? The same question that I asked for these plane drawings, now I'm going to ask about these shapes. Yes? They're all three-dimensional, very good. Now they're all solids in 3 space, they're polyhedra, yes? All the lines are straight this time, yes? That's also true for the polyhedra, yes? There are faces everywhere in the sense of?
You never have an edge or a vertex not
Every vertex belongs to a face. Every edge is lying on a face. This was also the case before. Yes, because these regions also contain... Yes, that's true. But to go one step back, they are also made out of vertices, edges, and faces. Okay, very good. Yes, these are, again, qualitative characteristics. Yes? Now they have volume. Yes, that's true. Now they're three-dimensional. They all have volume. Yes? Yes? Each vertex has at least 3 edges. Yes, very good. To make it three-dimensional. Yes? Yes?
Maybe the number of vertices plus the number of faces minus the number.
Maybe the same formula will still hold. Very interesting. That will be a quantitative observation. So let's count again vertices, edges, and faces, and maybe the formula will hold. You expect the formula to hold. So let's look at this. 4 vertices, 6 edges, and 4 faces. The cube, 8 vertices, 4 on the bottom, 4 on the top, 12 edges, 4 on the bottom, 4 on the top, 4 vertical ones, 6 faces. Here you add another vertex on the top, you add 4 more edges for the roof, and you add 4 new faces for the roof, but the top that used to be a face is no longer a face of the cube with the roof. So altogether you add 3 faces. And here, 6 vertices, 9 edges, 3 on the bottom, 3 on the top, 3 vertical, and 5 faces. And again, as you suspected, vertices plus faces minus edges is again equal to 2. This is Euler's formula. When I said Euler discovered the formula in the middle of the 18th century, that's the formula that he discovered. He discovered it in the case of polyhedra. He was looking at polyhedra, not at plane drawings. For us, it was easier to look first at the 2-dimensional pictures, and then we discussed the 3-dimensional. But he was looking at that, not at the 2-dimensional drawings. And he was trying to prove the formula directly for polyhedra. Okay, very good. But now we have to prove the formula for polyhedra. His first proof was wrong. It's difficult to prove it directly for polyhedra. Now we have to prove it. Let's prove that this formula always holds for every 3-dimensional solid, not just for these 4. Yes? Well, we have to prove it at some point, so if you can suggest.
It's a very, very good. I would suggest just stretching one face into a giant infinite face and then turning the whole thing into a planar drawing.
Aha, somehow stretch one face to a giant infinite face. Okay, and do the whole thing on a plane drawing. Yes, that's how we'll do it. Yes, yes. What were you saying?
I was just asking if you could repeat the...
If you could repeat it, it would be slightly more difficult to repeat it in 3 dimensions. Because, you know, how is it? It's more difficult to do it in 3 dimensions because it's just not as the way it works in 2 dimensions. But the way we're going to do it, as you suggest, is we'll flatten it on a plane. We'll reduce the 3-dimensional situation to the case of a plane drawing. And we'll do this via what's called stereographic projection. That's one of the most important pictures that you will see. If you continue as mathematics majors in the university, you'll see this picture appear over and over again in your classes. It's fundamentally important. What happens is you take a sphere, so let's say you take this sphere, and you place it on a plane with the North Pole up and South Pole exactly on the plane. Now, the North Pole will play a special role. The North Pole will be a special point on that sphere. And what you're going to do, for any point on the sphere other than the North Pole, you connect with the North Pole by a straight line. You know, if this is the North Pole, any other point I can connect by a straight line. And then you look at where this line intersects the plane. And you say that P goes to P prime. You project P to P prime. This is what we call stereographic projection. Every point on the sphere goes to a corresponding point on the plane. And we say P maps to P prime. P prime is the image of P. If you take another point, like here Q, again you connect the North Pole and Q, continue until you meet the plane, and this will be the image of Q. Q goes to Q prime. What happens with the South Pole? Yes? It stays where it is. If you connect the North and the South Poles, the South Pole is already on the plane, so it goes where it is. And conversely, if you take a point on the plane, it comes from some point on the sphere. Take a point on the plane, join it with the North Pole, and see where it intersects the sphere. This point will correspond to a point on the sphere. Now, this is very interesting. We think of the sphere as a plane together with the North Pole. If we remove the North Pole from the sphere, what we get is you can flatten it as a plane. Why is this strange? Maybe it looks strange because you think of a sphere as smaller than a plane. You can wrap up a sphere by finite area of duct tape, but you cannot wrap up the plane by finite area of duct tape. The sphere, in some sense, is finite. You can wrap it around by it has finite area. And yet, even though it's finite and the plane is infinite, the sphere has as many points as the plane. Every point on the plane corresponds to a point on the sphere, together with an extra point. I think of the sphere as larger than the plane. It's a plane. You take the plane, you curve it, and then you add even more points. You add the North Pole. That's, for many purposes, it's convenient to think of the sphere in this way. Made out of a plane together with the North Pole. Or you think of a plane as the sphere with the North Pole removed. Okay, now, under stereographic projection, what happens with a point which is close to the North Pole? If you have a point, here is the North Pole. And what if I have a point very close to the North Pole, yes? It's extremely far away. When you connect them, the line joining them is almost parallel to the plane. It's not parallel, but it's almost parallel, and it will intersect the plane somewhere very far away. Okay, now if you have a curve on the sphere, you project stereographically, and it will go to a curve on the plane. any shape on the sphere, let's say you have a continent on the sphere, you project and you get a shape in the plane. So from 3 dimensions, that's a very natural idea, you go to 2 dimensions. If you prefer, you can think about this as having a light source at the North Pole. And the image of any point is the shadow of that point. The point P casts a shadow, and the shadow is P prime. If you have any region on the sphere, you look at its shadow, it's a region on the plane. If you prefer, you can think this way. Okay, but now let's go back to Euler's formula. We wanted to prove that any polyhedron satisfies this magical relationship, vertices minus edges plus faces equals 2. And for this, well, we take a cube. Let's do it for a cube. Any other polyhedron will work as well. You take a cube. Imagine a light source at the beginning of the sphere. And then you look at the shadow of the cube on the sphere. In other words, you push it towards the sphere a little bit. So this is what we can call a spherical cube. It's a cube, the edges of it are pushed on the boundary, are pushed to the sphere. Okay, so this is now this cube. And we have to figure out if it satisfies Euler's formula, vertices minus edges plus faces, if it's equal to 2. What we're going to do, we'll do the stereographic projection. So let's do here. The North Pole is the top of this red region, and you see what happens with the faces of the cube. The meridians, some of the edges of the cube are parts of meridians, and they go to straight lines. If I have this sphere and a meridian, with stereographic projection, the shadow of a meridian circle will be a straight line. So some of them will go to straight lines, others will go to arcs of circles. But every region will go to a region in the plane. The bottom region suffers almost no change. Everything close to the South Pole doesn't go far away. The 4 regions on the sides, they correspond to these other 4 regions. And there is one region on the top, containing the North Pole. It will spread out to the infinite region. That's what you were saying when you said take one face and spread it apart, yes? Okay, by the way, with stereographic projection, the North Pole doesn't go anywhere, doesn't correspond to anything. But the face containing the North Pole, it corresponds to this outside exterior region. And now, from that cube, by stereographic projection, by looking at its shadow, if you place a light source at the North Pole, you get a plane drawing. For the plane drawing, any vertex of the cube corresponds to a vertex of the plane drawing. Any edge of the cube, now it's not a straight edge anymore, it's slightly curved. Any edge corresponds to an edge in the plane drawing. Any face of the cube corresponds to a face in the plane drawing. And in the plane drawing, vertices minus edges plus faces equals 2. We proved it. Therefore, it also holds in the cube, in the case of the cube. Every other polyhedron, take a complicated polyhedron, place it inside a bowl, put a light source in the middle, take the shadow. Now you get a drawing on the sphere. If you look at the shadow of the polyhedron, you get a drawing on the sphere, and then take the North Pole inside one of the regions, project from this tiling of the sphere, from this drawing on the sphere, you will get a plane drawing. The edges, vertices, and faces just correspond. That's why Euler's formula carries over to the 3-dimensional case. Again, Euler first proved it in the 3-dimensional case. And also, remember at the beginning I said, let's agree to call the points vertices, the curves edges, and the regions faces. The reason we call them this way is that this terminology is inherited from the three-dimensional usual terminology. For a polyhedron, you really call the points vertices, the lines edges, and these, the faces, they are faces. They're just called vertices, edges, and faces. And we inherit the terminology for the case of plane drawings. Okay. And also, you see why we decided to count in the infinite region. Because in this case, the infinite region is the top face of the cube. In the plane picture, it looks different from all the other regions. All of them are bounded. This one is unbounded. It's exterior, it's outside. But if you think about this as a stereographic projection of a cube, the outside region is just the top face of the cube. It's no worse than the bottom face of the cube. So why should we count the bottom face of the cube and not the top face of the cube? That's why we also counted in the exterior region at the beginning. Okay? Okay. Now, again to stereographic projection. And now we finish with a discussion involving a sphere and a life belt. Let's suppose that you're a buck, a small buck, crawling on the surface. Crawling on the surface either of the sphere or on the surface of the life belt. Now, you're very small and just crawl on that surface. Inside it's empty. Inside is just air. You don't have anything inside. You only stay on the surface. If you look from where you are, you can obviously tell that this is a life belt and this is a sphere. It's obvious. This has a hole in it. And all of you see that hole. However, if you're just crawling on that surface, you cannot see that hole. How are you going to see it? You're a buck walking here, crawling on the surface. You cannot fly out of it. You only stay inside. That surface, maybe it has some hills here and there, so it's some relief, but you can walk everywhere. It's finite. You can color it if you want. The buck is allowed to color it, but the buck cannot fly outside. Now I have a question for you. Is it possible, or is it not possible, for the buck, without leaving the surface, without flying out, to figure out if it is on the sphere or if it is crawling on the life belt? Is it possible for the buck to tell them apart just by looking nearby? The buck has a very limited worldview. Yes?
Well, he could do that by drawing a line vertical, so always scrolling down and then go up again, and then
here. Yes, but let's say that there are some hills here and there. So the buck doesn't really know how to go in only one direction because there are hills and it's slanted here and there, so the buck cannot keep that shape. You're saying if the buck draws a line here, comes back to exactly the same place, and then goes the other way, and if it's larger, then it will be on that. Yes, but let's say that there are some mountains or hills on the surface, so that the buck cannot keep a straight line at all times, cannot keep a straight curve. Maybe it goes a little up here, and if the buck goes, then this will bring it to the left too much, to the other side. The buck doesn't have magnets. The buck doesn't have notions of north and south. The orienteering is not a good skill for the buck. Yes? Yes, the buck can. That's a good answer. We can stop here because that's a very strong statement that the buck, just from crawling, can figure out. Okay, why?
Because it's actually exactly the same as our ancestors did it, because we live on a sphere and we couldn't fly out or something to see if it is a sphere, but because of the sun and how the shadows
I see. So the book can do it the way our ancestors did it, using the sun and the shadows. Yes, you know, in geography you study proofs like the Earth has the shape of a sphere, but I think these proofs were wrong. My geography teacher was telling me that you have to give 3 proofs to prove that the Earth is a sphere. 2 proofs are not convincing enough. But if 2 proofs are not convincing enough, 3 are not either. But the book doesn't have any notion of there are no planets, no sun. The book only crows here. Yes? Yes? Very good. Yes, the book can make a drawing of triangles. Very good. The book, let's say that the book is a spider. The spider can build a net, very tiny, tiny regions. Maybe some of them are triangles, maybe some of them are like rectangles, but the spider can build a net around the surface, and the spider can do it because it marks some region, it sees that it's a region, then it keeps going. The spider, even though it has very small world view, it can walk to every single point on that surface. So the spider builds a net. Very good. Builds a net either here or here. Okay, and after the spider builds the net, the spider can mark vertices, edges, and faces. Very good. And then the spider can count the number of vertices, can count the number of edges, and the spider counts the number of faces, as we did at the beginning for these plane drawings. Remember how we started the talk today. And then what would happen if the spider computes that the number of vertices minus the number of edges plus the number of faces equals 2? What can the spider say? Yes?
I'm guessing it wouldn't be true for the donut.
The question is whether this is true or not for the donut. Very good. For the live belt or for the donut. Now we have to figure out if Euler's formula also holds on the donut or if not. So a spider builds a net like this, but for us, let's do something simpler. Let's do this handmade spider net. You have one circle here, one circle on the other side, and 4 handles. So let's compute for this example. Notice what are the regions here. You have this from top to bottom, here again from top to bottom, this curve on the top and this curve on the bottom. This face is like a rectangle. And you have the same one. So this is the rectangular face. You have the same on the back. Look at this example. Of course, the spider will build something much finer than that, much smaller. But let's look here. Let's count. Here, how many vertices are there? Yes? 8. Very good, because here you see 4, and there are 4 on the other side. How many edges are there? Yes? 16. Why? You just count them. Yes, yes, yes. 1, 2, 3, 4 here. 4 on the other side. Here 4 on the inside. And here 4 on the outside. So 16 edges. And then how many regions? This is one region, one rectangle. And inside you have also a rectangle, which looks like this, except it's smaller and curved towards the center. Yes? 8. And what happens when you compute V minus E plus F on a torus? We call this a torus or a donut or a live belt. Doesn't matter. You get 0 rather than 2. Now, of course, I don't want to say Euler's formula fails. Such a formula cannot fail. It's too beautiful, too miraculous. It doesn't fail. It just takes this form. Euler's formula on the live belt takes the form that vertices minus edges plus faces equals 0 rather than 2. And this is how a spider can tell apart a live belt from a sphere. This is really the tip of an iceberg. In mathematics, this brings to really sophisticated, really conceptual mathematics. If you want to understand, let's say, the shape of the universe, this problem, this consideration is your starting point. Euler's formula is the starting point for that. We started with very simple math, just counting regions and vertices and edges at the beginning, and this is really introduction to very conceptual, very interesting, fascinating mathematics. I hope some of you will explore that in your university studies. Thank you.